All right, so I only have 6 slides to show you, and we're going to be using a face cam this time. So if you don't like it, I'll gladly take it away, but I think we'll be all right. And then after the slides, I will show actual code. Just be warned, it is using code from the last videos that are over a year old now, so, but it will still work. So, yeah. Okay. The compare instruction behaves like the subtract instruction. If you have learned that, I hope some of you have learned more assembly over the past year. So compare behaves like sub, but it doesn't modify the operands. It does set arithmetic flags though, which we will look at in a minute or so. And it sort of sets the stage for conditional jumps, which we are also going to be looking at. Unlike higher level languages with loops and conditional structures, assembly uses compare labels and conditional jumps. Yeah, a completely different world here. Just some fundamental stuff. 2 source operands, 8 or 16-bit operations. Obviously, again, we're sticking with 16-bit assembly here for the time being. You can either do regmem or regmem-reg. We can compare regmen and immediate value. So, yeah. The next instruction is the jump instructions, plural. That's CC behind the J. That means that there's multiple clauses for this instruction. JCC isn't an actual mnemonic. It's just saying there's a bunch of different jumps, which I have a table in the next slide to show. It's only one operand. 8-bit signed immediate acts as a relative offset to the current content of the instruction pointer. That's kind of a mouthful, isn't it? The assembler will calculate the relative offset when we use labels. But that's just fun info, I guess. So I actually forgot the flags register in my register video. Whoops. But it's so different from, all of the other registers because it's kind of like a meta register, or like a state, sort of like a state byte of a bunch of different things. It's 16 bits like the other registers. Some bits are not available to the programmer. The state changes based on outcomes of certain instructions. And certain instructions allow individual bit manipulation or entire overwrites of the register. So you can like clear interrupt flag, or you could push or pop the entire flag from the stack. Yeah. This is the bit representation of the flag register. This kind of deserves its own video, but we'll be using this stuff, as we start actually doing assembly, bootloader, OS stuff. Carry flag is at bit 0, parity flag at bit 2. Some bits aren't used. They're for other internals of the processor, or there's ambiguous. So please don't mess with them. only read and possibly mess with the letters in there. And this is a little table of all the different jump instructions. Surprisingly enough, there is some abstraction in assembly. Some conditional jumps use the same flag state, and it's up to us to decide the context. So like JNZ, JNE, jump if not 0, or jump if not equal. Technically the same thing, because it's both checking the 0 flag bit, which and now we do the fun part. Just a reminder, this is a video series, so if you haven't been following along, we're going to be using stuff we've made in the past videos. But if you have procedures similar to mine, then you can use those. You know, it's all right. We just might be doing things a little differently. So I've cleared the start label and between the jump $sign. That's where we're going to be doing our work. I'm going to use the CX register for the loop counter. So let's say I wanted to loop 10 times. I would start by moving 10 into CX. And you can name this whatever you want, but I'm going to name this for loop, this label, do the colon behind it. I don't remember if I explained the labels or not, but they're pretty easy. So this is where the compare instruction is going to come in. We're going to compare CX to 0. We're going to be checking if CX is 0 so that we can stop the loop. So now we need a way to actually get out of the loop whenever that checks it. So we're going to use a jump instruction, JE for jump equal, jump if equal. We're going to say and loop. That's what I'm going to name this upcoming label. And loop. Again, you can name it whatever you want. So this is good, right? We're on the right track here. Now we need to actually loop. So I'm actually just going to decrement CX. This is same thing as sub CX1. So it's just decrementing the value inside of CX by 1. So, and then we JMP, which is just a normal jump, normal short jump, back up to the for loop label. What assemblers actually do is they save the memory address of, you know, labels, or the relative address of the label, and that's what the assembler does. It jumps to that address in memory. So kind of like identifiers for variables, but not really, but they can be. Okay, so we can go ahead and save this and do our little assemble batch file, if you remember that. And cool, we have nothing. So this is where that hex print is going to come into play. All right, so we have our loop that is doing a loop, and that's it. It's not doing anything else. I can actually just push CX and then call hprint. Because remember, hprint will take what's on the stack. So, and yeah, we will assemble it again. Oh, I think that's 000B being printed a lot, but it should only print 10 times, right? Because we have a functioning loop here. I mean, there's nothing wrong with this, right? We only want this to print 10 times, but it's staying in the loop. Welcome to assembly. So when you call hprint, we're using CX and HPrint. The processor isn't going to reset a register when it returns from a procedure. It's not that smart. You have to actually program it. There's two ways you can do this. You can either make room on a stack or directly push pop on off the stack. I'm going to push pop in this case. It's kind of like saving CX, you know. So I'm going to actually push CX one more time. HPrint's going to use this first CX I pushed, and then now that's gone. Now I can pop CX, and it's like CX never even changed. So we're back to our CX that we need for the for loop. And then if I run this again, you'll see there's our counter counting down visibly. And again, we have our new line. So I could call new lines and make it a bit cleaner.